Swayam Prabha. Digital India. Educated India.
In the previous class, we studied continuous system for transverse vibration. We derived the equation of motion for a beam with distributed stiffness and mass property. We considered the Euler-Bernoulli beam model. Today, we will be extending the solution of that particular beam model using the finite element method. We already introduced the finite element method when we were discussing the torsional vibration, and on the similar lines we will be describing the finite element method for transverse vibration. And in this particular case, we will see that for transverse vibration for one element will be having more degree of freedom as compared to the torsional vibration case. So, the size of the matrices for the element will be slightly bigger. Earlier it was 2 by 2 matrix, but now we will see that it will get doubled, and even we will see that when this other effects like the gyroscopic effect and when bearings are there in which the plane of the motion in two directions are coupled, then the size of the mass matrix and stiffness matrix will be even bigger. So, with this let us see what are the things we will be covering in this particular lecture. So, basically we will be covering the transverse vibration using finite element method. Both the free and forced vibration we will be considering, and in this similar to the torsional vibration case, here various concept of finite element method like completeness, compatibility conditions, consistent mass and stiffness matrices will be deriving. Even we will be deriving the consistent force vector. So, let us take one beam. So, this is a beam, and we want to analyze this particular beam for torsional or transverse vibration using finite element method. So, we have divided this particular beam into various number of elements, and this particular beam element is one of the representative element. In this, we have defined node 1 and node 2, and you can able to see this particular beam element we have shown in one of the plane, that is zy plane. As we discussed in the previous lecture, in a Euler-Bernoulli beam, the single plane motion is that one plane motion is uncoupled as compared to with respect to the orthogonal plane motion. So, we can able to analyze the one plane motion separately, and the other plane motion orthogonal to this will be identical to that. That means z x plane motion will be we can able to analyze on the similar lines, because in this particular case element properties are same in these two planes. We can able to see that to define the position of this particular node, we have the linear displacement, also the slope we will be defining. So, the positive convention of the linear and angular displacements we have considered here. Similarly, at this node we have two coordinates, one is linear displacement or translational displacement, and this is the rotational displacement or the slope of the beam at this location. This is the basically one of the element of length L. So, you can able to see this is the small element of size L, and total length of the beam is capital L. Now, when we consider the continuous system, the continuous displacement variables we had was the linear displacement or translational displacement and the slope. Now, for this particular element, we have two nodes, and at nodes we have 4 variables. That is, these are the field variable for one element. So, 2 is translational and 2 are slope. And now, in finite element method, we will be seeking solution of these displacements, and if you want to know displacement other than the node position in this position, then we will be using interpolation function or shape function to interpolate the values of the displacement in between. So, that means the displacement at any other location z, this is in the local coordinate system, can be expressed as the shape function and the nodal coordinates, and in this particular case this nodal coordinates will be this, and shape functions will be accordingly we will be choosing subsequently. And as for the torsional vibration case, the shape function will be choosing based on the completeness and compatibility condition of the problem, and that will be choosing at the stage when we will be developing the weak formulation of the problem. So, for formulation of the weak form, whatever the assumed solution we have, the approximate solution of this form, in which this is the approximate solution. If this solution, if we substitute in the equation of motion of the continuous system, which we derived in the previous class, because the solution is approximate in nature, so you can able to see this equation will not satisfy completely. This will not be completely equal to 0, but some residual for that element will left out. This governing equation which we derived earlier was valid for each and every point onto the beam. So, obviously, it will be valid for a particular element also. So, that is why we have substituted the solution of the element on this. So, we got some residual, and using Galerichan method by multiplying the some weight, and in this particular case this weight will be the shape function of the problem itself. So, if we multiply the shape function with the residual, and if we integrate this residual over domain equal to 0, and as we know this shape functions will be equal to the number of coordinates, the degree of freedom of the elements. So, in this particular case we are substituting this residual in this expression. So, this is the expression for that. So, you can able to see this is the this inertia term, and this one is this term, and in this particular case I have taken out, if we have EI properties varying, then we need to write the equation like this that we have discussed earlier while deriving the equation of motion of the continuous system. So, if it is constant, it will come out, and we will be having derivative of v with respect to z 4 times, which we have represented as prime here, and here explicitly we have expressed in terms of the partial derivative with respect to z. And these force terms will be as it is. This is a distributed force, this is a concentrated force acting at z is equal to z naught location. So, we have substituted the residual here, and we are equating it to 0. These expressions are we have r number of such equations are there. Now, we will, because in this particular equation the highest order of differentiation is 4. So, for this particular case, if we want to choose the shape function here in the form of polynomial, so we have to choose a 4th degree, because the 4th order differentiation is there. So, unless we choose fourth degree, it will vanish. So what we will do in this particular case, we will weaken the requirement of this particular shape function degree by doing integration by parts of this particular term in which we have z derivatives. So, let us see. So, here I have expanded those terms. So, this is the inertia term, and this is the term which we want to do integration by part, and other terms will be as it is because they do not have higher derivative with respect to z. So, now let us see how we can able to differentiate this with respect to. So, I am differentiating, I am taking this term only. So, if we do the integration by part of this particular term, so this will be first part, integration of the second part, this is integration of the second part, limit 0 to z, L, 0 to L. This we are doing over the element length, minus 0 to L, differentiation of this particular first term. So, differentiation with respect to z I am writing as prime. This will be integration of the second term, that means same as this term. Dz. So, we have integrated, we have done integration by part of this once. We will be doing one more time, so that we can able to reduce the requirement of the this particular differentiation. So, if we do one more time, so this term will be as it is. Now, in this we will be considering this as first part and this as second part, and if we do the integration by part, we will get this as differentiation of the first part and integration of the second part. So, that will be this is okay 0 to L, and then this will be positive 0 to L, differentiation of first part, differentiation of this and integration of this. So, what we have done here, we have done integration by part of this in two steps. First was this one, and then second of this. So, if you see, finally you will get this. So, this expression will be as it is, there is no change. This first term is this term, and this particular term is this, and this integration is this one, and these four terms are unchanged there as it is equal to 0. So, you can be able to see that how we have done the integration by part twice to get the weak form of the formulation, finite element formulation. And in this particular case, now if you see, the highest order of differentiation is 3 or within the integral and outside the integral, and within the integral highest derivative is 2. So, the completeness and compatibility conditions now will be defining. First is in whole expression. So, whatever the highest derivatives with respect to z is there, up to that we require the completeness. That means, we need to have the polynomial which should satisfy that. So, you can able to see now with cubic polynomial we can able to satisfy this, this will not vanish. And for compatibility condition, we need to look into the within the integral what is the highest differentiation with respect to z. So, that is 2. So, as per rule we should have the compatibility one order less, that means up to first order. So that means we need to have compatibility at the common node of two elements of the variable itself and its first derivative, that means slope. So let us see this two requirements. So highest order of derivative with respect to z in the whole expression is third. So completeness of these are required, and so up to the third differentiation with respect to v, because this slope is itself is first differentiation of the displacement, linear displacement. So a polynomial of third degree is sufficient to set for the shape function or the interpolation function, and for the compatibility the highest derivative within the integral is 2. So up to one order less, that means the linear displacement and the angular displacement, we require the compatibility condition. So with this information, now we can able to decide about the shape function. So as we have chosen the shape function as approximate, and we had the nodal displacements in the element as these 4, because 4 degree of freedom element is there for two nodes. So we expect there will be 4 shape functions, and these shape functions, as we have seen in the previous condition, that cubic polynomial is sufficient to represent the shape function for this particular problem. So this expression we can able to write in a row vector and column vector like this. So we can able to see this a1, a2, a3, a4 are unknown. This we need to find out from the boundary condition of the element and let us see how we can able to obtain these constants. So we have obtained the weak form of the formulation, and based on that we have now chosen what should be the polynomial degree, and this polynomial degree polynomial is having 4 constants, and we will be obtaining this using the boundary condition of the element. And let us see how we can able to obtain this these constants. So this is a particular element which we have chosen. It is having 2 nodes at 2 ends, and at each node we have 2 displacements. One is v, translational displacement, another is the phi, that is phi, which is slope. So you can able to see there are 4 variables attached to this particular element, and the boundary conditions for this, considering this as a local coordinate system z. So origin is here, and this end is z is equal to L. So you can able to see at z is equal to 0, the translational displacement is v1, slope is equal to phi x1, this should be phi x1. Similarly here at z is equal to L, we have displacement v2, translational one, and the slope is phi x2. Now we can able to yes. So in this particular case, because we need the slope also, so this is the derivative of the shape function which we chose in the polynomial form. So if we take the derivative, we will get this expression, because one term, one degree will get reduced, and this itself we can able to write again in the similar form as the previous one. Only thing is we have now a4 0, but to take care of that we are keeping this as 0. So basically here in this particular expression only 3 constants are there, 4th is not contributing. Now we will be satisfying these boundary conditions. So at z is equal to 0, slope the displacement is v1. So if we satisfy here z is equal to 0, you will see that a4 will remain, other terms will vanish. If we put z is equal to 0 in the slope term, This two term will vanish, only A3 will be left out. Similarly, if we put z is equal to L in this displacement term, we will get these, and in the slope term we will get this. So, basically we have 4 equations and we have 4 unknowns A1, A2, A3, A4. So, and they can be solved because they are simultaneous linear equations. These expressions I have written in this particular form. So, you can able to see that I have expressed these 4 equation in a matrix form, something like this. So, we have A1, A2, A3, A4 is equal to V1, Vx1, V2, Vx2. So, the first equation, if you want to substitute here, we will see this will be 0, 0, 0, 1. The second equation will be 0, 0, 1, 0. This expression will be L cube, L square, L 1, and this expression will be 3L square, 2L 1, 0. So, basically put this in a more systematic way in a matrix, and this I am calling is at A, this is small a in the next slide, and this is the eta, that is nodal displacements. Now, these constants are unknown. So, we can able to get this by inverting A matrix. So, that we have done here. We inverted A matrix to get A multiplied by the nodal displacements, and if we invert the A matrix, the form of the A will be like this. So, we have obtained now A constants of the polynomial. Now, we earlier expressed this particular displacement, shape function displacement, as, we'll go back to this, we expressed like this. So, basically we had A here, which is now we have obtained as A inverse into eta. So, now we are substituting this in place of A, this quantity in this expression. So, that is the z terms and inverse A into nodal displacements, and if we multiply these two, we are expressing, because the size, let us see the size of these. So, we have 1 into 4 of the first row vector, and this is A matrix is 4 by 4. So, finally, we should get this as 1 into 4. So, only one row is there and 4 columns are there, and corresponding terms will be we have defined as the shape function n1, n2, n3, n4, and if we multiply this, basically this shape function, which is written like this, will get this form. So, if we multiply A inverse into this, we will get this. So, here we have this as n1 shape function, this is n2, this is n3, this is n4, which is function of z. And for slope also we wrote on the similar lines. So, here in place of A, we have substituted the value of A. If we multiply capital A matrix and this, we will get this, the differentiation of the, that is shape functions. So, these are nothing but differentiation of the n1 with respect to z and n2 with respect to z, etc. Now, the property of these shape functions are, as we have seen in the torsional vibration case, here the n1 will be 1 if we put z is equal to 0. So, in the previous here, if we put z is equal to 0, this will be 1, others will be 0. So, n2, n3, n4 will be 0. Similarly, for z is equal to L, n3 will be 1, z is equal to L, n2 and n1, n2 will be 0, only this will be 1, this will be 0. Similarly, for z is equal to 0 in the slope, so if we are keeping n is equal to 0, we will see that n2 prime will be 1, others will be 0. So, here n2 prime is 0 1, others are 0. Similarly, for z is equal to L, we will be having n4 prime as 1 and all other 3 terms will be 0. Now, let us see the two elements. Basically, we are trying to see the compatibility condition at the common node. If we predict the displacement from this element and this element, whether we have the similar prediction of the translational displacement as well as slope, because we have seen earlier we require for this particular shape function compatibility up to the first derivative. So, this is the shape function which is predicting the displacements at the node position, also at the intermediate position. So, we will be using these two expressions to predict the displacements at the common node by two elements, two separate elements. So, for z is equal to L for first element 1, that is a z is equal to L. So, we are getting, if we substitute in the previous expression, this expression z is equal to L, we will get only this as 1, others are 0. So, we will get v z plus 1 and slope we will get phi x z plus 1. So, this is for element, in this particular case jth element. This is jth element. Now, for j plus 1 element, this is the expression. So, this for j is a z plus 1 element, this is a linear displacement and angular displacement. And in this particular case, if we put z is equal to 0, because for z plus 1 element, this common node is at z is equal to 0. So, if we put z is equal to 0 in this expression, we will get this as this here only this will be 1, remaining terms will be 0. So, this will give v z plus 1, which is same as the previous displacement from the element j, and if we put in this z is equal to 0, we will get this as 1, other terms are 0, and from here we are getting phi x z plus 1, which is same as the previous predictions these. So, that means from two different elements at the common node, this shape functions are giving same translational displacement as well as slope. That means they are compatible up to that. And if we want to check for higher order, then we will see that this may not be, this shape functions may not be compatible for second derivatives. So, if we take derivative of this once more and predict the value at common nodes from these two different elements, we will see that they will not match. So, with this, so now we have chosen the shape function of third degree, even we have obtained the explicit form of the shape function. We even check the compatibility condition of these shape functions, that they satisfy not only the translational displacement, but also the slope compatibility between two elements at the common node. So, now this approximate solution which we obtained in the explicit form, now we will be substituting in the our weak formulation, and then we will try to get the elemental equation. So, we if we substitute, so this particular equation is basically what we have done here. Earlier we had weak formulation equation that was I is equal to up to r. So we had r number of equations. Those r number of equation in the weak form, now we have put in a matrix form. So that means in that particular equation, if we look back that particular equation, we will see that in this expression n is containing the subscript I, which is varying from 1 to r. So only n are there. So these r number of equation we can put in a matrix form. So basically this n is a vector, which is, because now we know the r is equal to 4 for the present problem, because degree of freedom of the element is 4. So we have 4 shape functions. So here it was double derivative. So comma double z is representing the double derivative of n with respect to z. So this is shear force, bending moment. These terms I will be explaining explicitly. This was the force term. So now let us see what is shear force expression. So we had, after integration by part, this kind of terms. So I have represented the first term after integration by part like this. Here also, because n was having subscript 1 to r, so they are in a vector form. Now similarly, this one, the bending moment is from the second term we are getting it. Now let us see what we are getting from this. So if we substitute z is equal to L here, because n1 will be 0 there, so that expression is 0. For z is equal to 0, n1 is 0, so we are getting this one. And this I am expressing at z is equal to 0. This particular term is basically shear force, because here you can able to see this is a prime z, that itself is representing that the term within the bracket is differentiated with respect to z. So basically this is shear force term having third degree in the translational displacement. So I am expressing that negative of that term as shear force y1. Here we will see that for z is equal to 0 and z is equal to L, n2 will be 0. So this will not contribute anything. Similarly here n3 will be 1 for z is equal to L. For z is equal to 0, this will be 0. So this will contribute only one term, and that I am expressing as minus of sy2. So I have defined this sy2 as minus of this. So these are the shear force at node 1 and 2. Similarly, from the bending moment, we will see that the first and third term will not contribute anything. This will contribute, and they will belong to bending moment at node 1 and node 2 of that particular element. So coming back to the previous equation, in this particular expression, we have seen explicit form of these two. Now, because this is the displacement we have chosen in a form of shape function like this, and for the nodal displacement. So this is for the element, this is for the nodal displacements. So this approximate solution we are substituting here. So once we substitute, we will see that multiplication of another row vector of the shape function will come, and this particular term nodal displacement will get the derivative of the v with respect to time, because this is independent of z, so it will be outside the integral. Similarly, from second term we will get the derivative with respect to z, which was there in v will get in the shape function, but this eta will be outside the integral. This will not get any differentiation because there is no differentiation with respect to time in the second term. Similarly, this is basically we have clubbed the shear force and bending moment in one. There is the reaction force vector represented, and if you see the shear force which we got and the bending moment we have kept in a single vector, and this is the force term. So now we will be representing this term as mass matrix for the element, and this term as stiffness matrix for the element, this one, and this is the external force belonging to this particular vector and reaction force belonging to this. These vectors nodal displacements are these. This external force we are already expressed like that. So, you can able to see now we have got the elemental equation of the finite elemental equation of, and now let us see the explicit form of these mass matrices and the stiffness matrix. So, stiffness matrix as we have expressed the integral. So, this if we multiply these two vector, if you substitute and multiply, we will get this, and each term we need to integrate with respect to z, because we know this shape function in the form of z. So, if we do the integration of each terms, we will be getting the stiffness matrix like this. This will be a symmetric matrix, only shown the one half side of the diagonal. So, it is symmetric. So, we can able to write the other half without any problem. Now, let us see for a typical stiffness, let us say element K12. So, we need to substitute that corresponding shape function and their second derivative, and if we integrate, we will get that particular term. Similarly, we can able to integrate other terms. Now, coming to the mass matrix, we have these two multiplication. So, if we integrate these terms, we will get this as mass matrix. This is also symmetric matrix and is fully populated, and that is why we call this as consistent mass matrix and consistent stiffness matrix. One particular mass matrix, if we want to integrate, we can able to. So, this particular term is M12. So, this we will able to get. So, if we multiply these two, we will get that particular term from this. This is a consistent mass matrix because all the element of the mass matrix is fully populated. Now, we have obtained the mass matrix and stiffness matrix in explicit form. We have seen that in the right hand side we have reaction torque, a reaction force that contains the shear force and bending moment, but there is an external force also. So, if we know the explicit form of the force, then we can able to calculate that particular vector. So, let us try to calculate that vector for a particular distribution of the force. So, in the first case, let us say if we want to obtain the consistent load vector for uniformly distributed load, that is so Ft is a load which is uniformly distributed over the element. So, this is the load per unit length. So, if we substitute this in the distributed load component, there is no concentrated force because that was containing two terms, one was distributed and another was concentrated. So, this is only we are considering the distributed one. So, that force multiplied by the shape function term was there, and shape function term are having 4 terms. So, because this is a constant quantity, so it will go out, and we need to integrate these shape functions. If we integrate, we will get the consistent force vector for a distributed force like this. So, you can able to see that because of this distributed force over the element, we are getting some kind of equivalent force at two nodes as well as equivalent moment at those two nodes, because the first and 3 belongs to the force and second and fourth belong to the moment. So, for uniformly distributed force, we need in finite element method, basically we seek the solution at the nodal position. So, we need to obtain the equivalent of this distributed load at the node position. So, this is the equivalent of that. If you see, if we sum up the first and third term, that will give the total load. So, the Ft half and this is Ft half. So, this if you add it, that we will get Ft into L. So, that is the total force acting, but apart from that we are getting some moments also. And because there is another model in which instead of consistent load vector, we could have used the lump force model, in which obviously the straightforward will be that whatever the force is acting on this element, half of that if we apply here, half of that if we apply here, that is the lump force model. And in that particular case, this is fine, but moments will be 0. So, that will be the in fact inconsistent load vector or lump mass load vector. Let us see some more cases. So, if we have single concentrated force, so if of this form at z is equal to 0. So, let us say for one case it is at node 1. If it is at node 1, we can able to substitute here, because it is acting at node 1, that means that z is equal to 0. So, we know that this direct delta function, if it is there, if you want to integrate this term, because this is constant, this will go out, but this function will be evaluated directly by putting z is equal to z naught. So, that is basically the explicit integration of this. And for first case, when z naught is at 0, this one, we will see that only this will be 1 or this will be 0, because n 1 is 0 for rest of the case except at n 1. So, you can able to see that directly we are getting the nodal force at 1. Similarly, if node force is here, we will, if we substitute there, we will get at corresponding node, because second and third is fourth is for moment. This is for the force at node 2. But if we keep this particular force at the middle, then you will find that all the terms, including the moments terms, will not be 0, and this is a consistent force vector for the concentrated load. So, half of this is coming here and here as a force, but apart from that moments are also coming. So, you can able to see what is the advantage of the consistent force vector, that it is more accurate and is not based on the lump force analysis. Another case, let us say if the force is linearly varying like this, amplitude of this are given, and because it is linearly varying, so let us express the force as a linear polynomial where a and b are constant to be found out from the end condition of the force distribution. So, at z is equal to 0, the amplitude of force is F1. So, if we substitute here, we will get A is equal to this one. For z is equal to L, here the amplitude is F2, and if we substitute in this polynomial, we will get this. These two equations will give us A and B like this, and if we substitute A and B in this polynomial like this, then we are rearranging F1 and F2 terms separately. So, you will see that basically we obtain a shape function for the force. These are for node 1 and 2, but this is the shape function for force, and this can be used now for calculation of the consistent load vector. And So now we have, instead of force, we have kept this shape function into this. So not only the shape function of the element is there, but shape function of the force is also coming. This is coming out because this time dependent term. So if we integrate this, we will see that we will get the consistent force vector for linearly varying force like this. So at each, so this is the force, these are the moment. So this so this is a consistent force vector for linearly varying force. This analysis, now you can able to see that we can able to extend for if this distribution is parabolic or cubic or the similar lines. Now we have obtained force vector, also the mass matrix and stiffness matrix. So once we obtain the elemental equation, now the thing is how we can able to assemble if various elements equations once we have written, how we can able to assemble them, and especially if apart from the element which we have considered, if some concentrated mass like disks are is there, how to incorporate in the assemble equation. So let us see the assembly of the equation for very simple two element case. So in this particular case, we have two elements. So this is one element, this is another element. The dimensions of these two elements are different, and in between this there is a thin disk. So now you can able to see that in these two elements we have three nodes, 1, 2 and 3, and at these three nodes we have, at each node we have 2 degree of freedom. So total 6 degree of freedom is there. So we have divided this two elements like this. So disk we are keeping with the first element. The second element we are not keeping the disk. This disk we could have kept here, but only thing is we need to keep it one of the element, because once we join back these two elements, we should have only single disk mass contribution. So in this particular case, we have kept the disk in the element 1. So you can able to see that various reaction forces and moments, shear force, and that is coming. So now we can able to write the elemental equation for these. So let us say this is the elemental equation for first element, this for second element. Various individual mass and stiffness matrices are given here. So for element 1, this is the stiffness matrix, this is the mass matrix. So you can able to see that because at node 2 we have concentrated mass, that is a point mass. So that's why in diagonal term mass of the disk is also appearing apart from the mass of the shaft. So other terms are belonging to mass of the shaft, only this term is from the disk. Diametral mass moment of inertia of this disk is not considered, otherwise it could have come here. You can able to see in the element 2 because the dimensions of the element 2 are different. So this stiffness matrix will be different as compared to element 1. Here only mass from the shaft is coming, not from disk for the element 2. Now these equations, now let us see the nodal displacements. So this is corresponding to element 1, and this is corresponding to element 2, and this is force vector for element 1 and element 2. And if we assemble them, this is the assembled equation for that. So you can able to see that this 4 by 4 is for element 1, but because there is a common element, so we have some of the terms related with the common elements of the two elements are coming. So you can able to see these are for element 1 and these are for element 2, and this mass of the disk is also there. Similarly, this is the assembled equation of the stiffness matrix. So you can able to see with the subscript 1, they belong to element 1 and this belong to element 2. So this is the assembled equation, and the nodal displacements, because there are 6 degree of freedom, that many will be there. Shear force and bending moment, the reaction force. So, obviously, they will cancel at the common node, because once we assemble these elements, they will cancel each other. So, now once we have obtained the assembled equation, now we can, depending upon various kind of boundary condition, we can able to solve this problem. So, in today's lecture, we started with the development of the elemental equation. We used Galerichan method for the development of the elemental equation. In the previous class, we developed the Euler-Bernoulli beam equation of motion, and for that particular case, we started the approximate solution, and we obtained the weak form of that particular equation. Based on the weak form, then we obtain the shape function in the explicit form, and once we obtain the shape function, we use that for obtaining the explicit form of the mass matrix and the stiffness matrix. And through some cases for the force vector, the consistent force vector, we have seen that how the force vector takes the form if it is uniformly distributed or concentrated force or linearly varying force, how this particular consistent force vector takes the form. And then with a simple 2 element case, I try to explain how the assembly of these elemental equations can be done. Now, in the next class, we will see through some example how we can able to solve the calculation of the free vibration or forced vibration for a particular boundary condition of the problem, because till now for when we are developing the elemental equation, we did not consider the boundary condition of the problem as a whole. So, in the next class, we will take up some example in which we will be obtaining the natural frequency of the system as well as the forced vibration of the system using finite element method.